Lesson 4.7, Geometry. Congruence transformations. Students are working on the warm-up problems. If you're still working, keep working. I'm just going to start to feel like number one's a pretty simple one, so I'm going to start there. But if you're still working on number two, keep on keeping on. All right, number one says, if triangle MNP is an equilateral triangle, find the values of x and y. That tells me two things about my triangle. That tells me all the sides are the same length. All equilateral triangles are also equal angular, so it tells me all the angles are the same. And more specifically, each angle measures how many degrees? What'd you say? They all have to total 180, so they each have to be 60. Yep, they're all 60. Okay, we know all of that just based upon the fact that it's an equilateral triangle. So to find x, which is a side length, I see side MN is 14, so you would just set 3x minus 4. We know that also has to have a length of 14 since it's equilateral. Add over the 4, divide by 3, should have gotten x to be 6. Now to find y, we know that all the angle measures are 60. There wasn't anything to really like set this equal to another like expression or anything. We know it has to be 60 degrees. So add over 5, divide by 5, we got y to be 13. Okay, and lesson 4.6, we were talking about equilateral and then also isosceles triangles. So the next one's an example with isosceles triangle. Okay, so if you tried this one, let's see how we did. It's always helpful to draw a picture. Triangle JKL is an isosceles triangle with vertex angle K. All right. The vertex angle is the one that's across from your base. So isosceles triangle means that two sides are congruent. So I'm going to call this one angle K. I'm just going to mark it like that. It's not congruent to anything, but it's across from my base, meaning these are my two congruent sides, JK and KL. That's what that means with vertex angle K. That those two sides be my congruent sides. So it says, find x and y if JK is 8x, KL is 13x minus 15, and then they told me the measure of angle KJL, this one, is 5y minus 3, and JKL, that's my vertex angle, is 76 degrees. All right, so that was basically everything I was given in the problem. So now again, the x's are representing side lengths. So since I know those are my two congruent sides, to solve for x, I would just set these equal to each other. Minus over the 13x, we get negative 5x equals negative 15. Divide by negative 5, we get x to be 3. All right, solve for y was a little trickier. There's like kind of a couple ways you could tackle this. I think what made the most sense in my head was I knew all those angles had a total 180. So I took 180 and I subtracted off 76 because I already knew that my vertex angle was 76. So I'm like, okay, I have a remainder of 104 degrees kind of like left. 104 degrees kind of left in my triangle between these two angles. Now, in isosceles triangles, if these are congruent sides, what does that tell me about the angles across from them? They're also congruent, exactly. So if there's 104 degrees kind of like left between those two, they're each how many degrees? 52, yep. They each have to be 52. Or you could have done 5y minus 3 plus 5y minus 3 has to total 104. You could have done that as well. But I know that each of those have to be 52 degrees. That'd be another way you could do that. Okay, however you chose to do it, we should have gotten y to be 11. Okay, so that's a review over 4.6. So the quizzes I gave you back today, those are over 4.3 and 4.4. So last week we did 4.5 and 4.6, which means tomorrow, we have another quiz. Okay, over 4.5 and 4.6. I have a review sheet. Don't let me forget to pass that out. And there's one problem on the 4.6 bookwork I want to go over at the end of class, because this lesson's pretty short. So today, we're kind of working off the congruent triangles, but we're talking about congruent transformation. So first we need to understand what a transformation is. So I kind of wrote out this definition for you in your notes. A transformation is a function that moves or changes a figure in some way to produce a new figure. So we call the original figure like its pre-image. We do some type of transformation to it. We can shift it, we can slide it, we can flip it, we can dilate it, make it bigger or smaller, and make a new figure called its image. So a transformation can change the position, so if we like shift it around, it could change the size if we dilate it or like stretched or shrunk it. Could change the shape, the orientation, which way it's like facing. Those are all examples of like transformations. A congruent transformation then is a transformation that changes the figure, but the two figures are still congruent. Also called an isometry or rigid transformation. We call them congruence transformations in this textbook. But if you take like a triangle, and if you move it from this position to this position, you don't change the shape or the size, would those two triangles be congruent? Yeah, you're just changing where it's located. That's a congruence transformation. If the image is congruent to the pre-image. So today we're only going to learn congruence transformations. We're only going to focus on congruence transformations. So this chart's on the next page of your notes. So I didn't give myself a lot of room, but you guys have some room up here. I want you to just label these. These are all types of congruence transformation. There's 3 of them. Okay. 3 congruence transformations, meaning it doesn't change the size or the shape of the object. We're going to look at some triangles. I also threw in a couple other examples. Okay, the first one. Have you heard of a translation before? Yes. Okay, I see one guess and nobody else responded. Thanks, Gwen. Translation is a transformation that moves every point of a figure in the same distance in the same direction. It's also referred to, so the synonym for this is like a slide. So if we think about triangles, look at this blue one is like the pre-image, and the arrow showing you that it's just translating. This green one is called the image. So once I just take this blue triangle and I slide it, technically called translation, to a different position, would these 2 triangles still be congruent? Yes, the exact same triangles. That's why it's a type of a congruence transformation. Okay? Same with these backwards E's. Took this one and I just slid it. Maybe I went right and down, however you want to call it. That's a translation. It's just like a slide. A daily life example. Anybody play like checkers or chess? I like to think of chess because that's how the objects move. They can move in like the L shape, right? That's a translation. When you're moving the game pieces on the board, does the size or the shape of the piece change? No, you're just changing it to a different position. The 2 pieces would still be congruent from its pre-image where it started to its image by just doing a slide translation. Okay, the next one is a reflection. So this is a transformation that uses a line to reflect the figure and like mirror image it, and it's called the line of reflection. All right, so you probably did these in like elementary school where you took like a piece of paper and you put some paint here, and then you folded it and you open it up. You're like, it's the same shape on both sides, right? You guys remember doing that?
Yes.
Gwen, you're the only one who has long-term memory. I know this about you.
I remember. I did that.
You did that. Okay, so if I were to do this, The two figures would be the same on each side. Like, think of a triangle. Think of here's my piece of paper. If I were to fold it there, I would get the same triangle, but it's like orientation is different, right? So it's like kind of like opening up a different way is the way to think of it. Like this also, if I were to take this E and like fold it over that, this is called our line of reflection. You can write that down. Line of reflection. Would that still be two congruent triangles? Yeah, it would still be congruent. All the sides would still be the same length. They're just kind of like facing a different way. So you might see this as like a flip is another way to think of this. It just gets like flipped over some line of reflection. A daily life example is like a mirror. It reflects back your image. Okay. And then our third one is a rotation. So this is a transformation in which a figure is turned about a fixed point. You can kind of see this example right here. If I were to take this and I kind of turn it about this point in this angle right here, which rays can be drawn to form the angle of reflection. So this is the angle of reflection. Or sorry, angle of rotation. I think I said reflection. Angle of rotation. So you can see that it's not necessarily like flipped, like a reflection, but it's almost like turned over on its side. Okay, so another synonym for rotation is like a turn. The daily life example I came up with, this one was like the hands on a clock. Those just like rotate around and around and around. I don't know if you rotate like anything. It's just rotating at about like a fixed point. So you can see this heart. It's not a translation, right? And just slide it. It's not a reflection because there's no like line. I could fold this over and get the same image. But I just turned it on its side a little bit. That's a rotation. So it's like turned about some fixed point down here. Now let me ask you this. Are these hearts still congruent to each other? Are the size and shape still the same?
Yes.
Yeah, same with these triangles, right? I could still calculate the distance. I'm not changing the size of the shape. I'm just changing like its orientation in this case. That's what a congruence transformation is. Okay, let's practice some on a coordinate plane. And I threw in some triangles and then I threw in some other shapes too. So it says identify the type of congruence transformations shown. There can be more than one. So the pre-image is in blue. I know yours aren't color coordinated, but the pre-image is in blue and the image after the transformation is in green. So look at this one. It looks like a house. It's really a pentagon. It's 5 sides. But did the orientation of this change? Did it get like flipped or turned? No. And the arrows here are showing you that it's just sliding from one position to another. So this is just a translation. Okay. All right, this one. I have two kind of like different orientations, right? It's not like I just took this triangle and slid it over here. It looks like it got like turned. It didn't get flipped though. If it were reflected, you don't have to write this down, just look here for a second. If this were to get reflected, it would look like this, just like backwards, like a mirror. It would look like that. That'd be like a reflection, okay? And you can kind of see they're showing you this angle of rotation. So this one, the fact that it kind of like got flipped or turned on its side, that's a rotation. Okay, so those ones are pretty easy to see. The next two, there's more than one. So it gets maybe a little bit trickier, but let's take a look at those. Okay, let's kind of go through our list. Could we classify this as a translation? Yeah, we could. We could classify that as it just like slid down diagonally. Another way we could classify this is we could do like 2 reflections. Okay, let me show you that. Could also say 2 reflections. Translation is probably like the best answer here, but if I were to reflect this maybe over like the x-axis, so picture like folding your paper right here. If I were to reflect it, it'd be here. And then if I were to reflect it again, or then fold it on the y-axis as my crease, do you see how it could end up here? Or the other way, we could reflect over this one, end up here, and then reflect it, like flip it over that way. You could technically call that 2 reflections. Somebody asked last time if we could call this a rotation, and I feel like we can't really. I mean, you definitely like could like take this and like turn it to get to there, but I don't think we could get it to this position. Like there's no center that would get me like to there. Because if my center was like here, then it rotated around like that point. Oop. Maybe we could. That point. Could it come to that point? My origin was the... No, that's 2 away. That's 3 away. It'd have to be kind of something around here. Anyways, I wouldn't really call this one a rotation because... Oh my gosh, I'm so over this part. All right. This one's a cool example. What's one thing I could call it? Could call it a translation, right? Just like shift it down. Could call it translation. What's another thing? Could call it a reflection over the x-axis, right? Do you agree? If you were to fold it, we could call it a reflection. What about rotation? Yeah, could also call it a rotation. This one would be like definitely about the origin if you were to like turn it. You can picture that getting to that position. So that could be any of them. Okay. Here's an example on a coordinate plane. Let's look at a couple examples. Not on a coordinate plane. Some real life examples. Okay. First one I have for you is a Van door. Same thing, identify the type of congruence transformation shown in the diagram. Reflection, translation, or rotation. What do we think for the Van door? Translation, right? Like a sliding Van door, translation. Really quite funny story. I don't remember how old I was, but I have 2 little brothers, and I was holding like the van door like this one time, and one of my brothers slammed the sliding door on my fingers, and my fingernail fell off, and my parents were like, put it under your pillow, maybe the nail fairy will come. And it did! The nail fairy came, I got $1. Isn't that kind of funny? Now I think about it, I'm like, that's gross. But yeah, I got $1 for it. He probably felt bad. He didn't do it on purpose, so. All right, next one. What about these feet print in the sand? What do we think?
What?
Yeah, reflection, right? That kind of just like flipped. Good. All right, so we can visualize those. We only have one last problem to do. Triangle PQR with those vertices is a transformation of triangle JKL with those vertices. Graph the original figure and its image. Identify the transformation and verify that it is a congruence transformation. All right, so my like pre-image or my original here is actually JKL. So I'm going to do that one in blue. -2, 0, -3, -5, -1, -4, JKL. So there's my original. And then it says triangle PQR is a transformation of that triangle. So let's go ahead and graph PQR. I'm going to do that one in green. P is 4, 2. 3, negative 3. R is negative 2. P, Q, R. Okay. So then it says identify the transformation, and then we'll verify that it is a congruence transformation. What type of transformation do we think here? Translation, right? The like orientation didn't change. It just looks like I shifted these points kind of like up and to the right. So translation, you can write that right underneath here. Any ideas of how I could verify if it is a congruence transformation? Side, side, side in the distance formula. Because basically you're just trying to prove that these two triangles are still congruent after we apply this transformation. Okay, I feel like you guys are pretty good at distance formula, right? So no one feels cheated if I tell you these distances? Okay, I did them all for you, don't worry. So first I did JK. And you'll get practice on your homework. Now I got that distance to be the square root of 26. So then I did PQ, distance formula, and I got the square root of 26. We're off to a good start. These two sides are congruent. Okay. The next one I checked was KL. So this little side, KL, and I got the distance to be the square root of 5. So then I did QR. And I got that distance to also be the square root of 5. So you're like, okay, good. So far, it's looking like it was a congruence transformation because these all have the same distances. They're just in different positions. They're just shifted. Last one we got to check, JL. I got the square root of 17. And PR. Got the distance to be the square root of 17. Good news. Those triangles are congruent, which verifies that this transformation indeed was a congruence transformation because the triangles are congruent. You don't have to write the congruent statement. You can if you want to, but you just have to check all the distances and make sure that those two triangles are the same. That's it. Okay, I do want to go over one problem on the 4-6 bookwork. So if you've started it, I'm going to do number 39 for you. If you haven't started it, take out a piece of paper and you can number 39 so you can skip that one later. The reason why I want to do this with you is because the algebra is a little tough, but it's nothing you haven't learned. And this is a great like plug of like why math is like so sequential. You've solved equations that have y squared in them before. You do it in algebra by factoring. Factoring, one of my favorite F words in math. But it's been a while. So I just want to do one of them with you. And 38 is similar, but 38 is actually a little bit easier. Okay, so I'm going to do the harder one. I'm going to do 39. And your textbook, since you've taken algebra, just like assumes you know how to solve this because you do in algebra. And I just know it's been a while, so let's do it together quick. All right. So this is the isosceles and equilateral triangle bookwork. And so you can see here we have an isosceles triangle with these two congruent sides, meaning these two angles across from the sides are congruent. So not these two, but these two. All right, so there's two ways you can kind of set up this equation. We know that this vertex angle, this y squared minus 62 degrees, plus these two angles, so you could either write out 2y minus 5 plus 2y minus 5, since these are congruent, or you could double 2y minus 5. We know that they have to total how many degrees? 180. Okay, so hopefully we could kind of like get that far. Here's the tough part. It's like solving this when you have a y squared and you have a y. So first I would distribute this 2. And I get to here, y squared minus 62 plus 4y minus 10 is 180. And then you'd probably combine these like terms to get y squared plus 4y minus 72 equals 180. Okay, here's a tricky part. You're probably tempted to like add over the 72, but I can't really like take off the layers around y here because can I add y squared and 4y together? No, these are not like terms. So we have to have another strategy to solve this. We call these like quadratics. That sounds familiar from algebra 1. And we have to factor to solve them. So you actually have to set them equal to 0. So negative 72 minus 180. I'll explain why in a second, is negative 252. Okay, so my quick review of algebra without going too in depth is that when you're factoring, you're basically just undoing the distributive property. So when I have something like this that has 3 terms, it factors into 2 binomials. Binomials meaning 2 terms. And I don't know how you were taught this, it could be different. But if I have y squared here, the only way I can multiply to y squared would be y times y. And then the strategy we do to factor this, to undo the distributive property, is you find 2 numbers that multiply to this constant. In this case, it's negative 252. You find 2 numbers whose product is negative 252, who add to b and add to 4. And if this factors, and both of these do, there's always going to be 2 numbers here. So this, you kind of just have to take your calculator and start doing 252, divided by, I don't know, 16, and I'm like, oh, I get 15.75. That's not it. 252, oh, maybe divided by 18. Oh, 18 and 14. So how could this work? 18 and 14 to multiply to a negative, one has to be positive, one has to be negative, but add to positive 4 would be 18 and negative 14. Do you kind of remember doing this in algebra? Okay, so in your calculator, you can do 18 times negative 14 would give me that product. You guys agree that 18 plus negative 14 is 4. So these 2 numbers go here. So you get positive 18 and negative 14. So here's what factoring is. If you were to like FOIL this out or multiply this out, you do y times y, which is y squared. Negative 14y plus 18y would add to 4y. And then you multiply these and you get negative 252. Okay, it undoes like FOILing, undoes the distributive property. Here's why we set it equal to 0. This helps you solve it. 0 product property. If you have a product that equals 0, the only way we can get a product of 0 is if one of these factors is 0. So then you kind of set up like too many equations for yourself. You're like, okay, well this factor could be 0, or this factor could be 0. And then you solve. This one you subtract over, you get negative 18. This one you add over and you get 14, and you get 2 possible solutions. Now, if you notice, the answer key just says 14. Any idea why? Ooh, Gwen. Why? Can have a negative angle in a triangle, right?
Yeah.
Look here. If I were to do 2 times negative 18 is negative 36, minus 5 more, I have a negative angle. That doesn't make sense. So 14 would be my only solution there. Okay. Now, as I mentioned, 38's actually like easier than that, but you do have to factor to solve it. So use this one to kind of try and help you factor it, but it is something you've done in Algebra 1. A lot of people in my 7th hour got stuck on that, so I just wanted to go over one. Okay. Pause the recording quick, and I'll pass out all the fun